Yeah, I hope nobody falls asleep, including myself. So ODL is in many ways related to a couple of projects that we have heard about today. Actually, perhaps a bit more general than some of the others. So although by far the main application is tomography, specifically CT, it is why does it show this? Okay. It is very much a mathematician's project and should allow defining, very broadly speaking, formulating inverse problems. And the thing that is maybe different from what most other projects do is that it tries to keep the operators abstract. And yeah, in particular, that it decouples any discretization that is needed for getting it to work numerically from the algorithm that works on the elements of these spaces. But yeah, in practice, this is very similar to what in particular SIL does. So the problem is you have some sinogram, and you know that ASTRA can implement a ray transform that should give this kind of sinogram, and you want to know what. And then what ODL offers is various solvers, which you can approximate the inverse of such a transformation and thus reconstruct whatever might have been in the original image. And there's a particular focus there on non-smooth solvers. So this example is simply filtered back projection, but that's the most of the ODL code base about what it's about, implementing many different solvers, but generally not the forward operation. So yeah, we're mostly using ASTRA for this purpose, but in principle, this can, as I said, be also something not related to tomography at all. Again, a little bit more on the philosophical side to set us apart from other projects. So ASTRA is kind of in between two extremes of how you might formulate problems, and the one that is the basis of what most people do in this kind of applications is that they do everything on arrays. And of course, the whole topic of this hackathon is different kinds of arrays. But we should keep in mind that there's also the possibility to do it much more like you would do it on paper when you even formalize your algorithms. And that is that you talk not about any array, but you talk instead about a particular mathematical space, a function space typically. And then you can define something like a Fourier transform on this function space without making a reference to any particular discretization. And then the discretization becomes a separate argument. And ODL does not quite go that route. So it's in the structure of the code you write, it's still more close to this array-based idea, but it does give more meaning to the objects that you're declaring. So in ODL, you're declaring an element of a space as an object of a class. And although this class or the objects contain, of course, arrays that somehow tell you the geometry that has been discretized here, this is then not itself an array object, but it's an element of, I'll show a bit later how this works. And then you can, assume that this space knows the geometry, and it's not just that it has been sampled in some way, but it still knows what kind of axis you are starting from, and so on. And as a result, you can then have something like a Fourier transform in a also much more abstract sense, where it just knows that for this particular space, the Fourier transform will have it has to obey the geometry that this space has. Now, how this is actually structured, we have at some level, of course, arrays, but the user seldom sees this. So as a user, you first declare your space, and this is a class. And yeah, it typically ends up being a representation of the mathematical Hilbert space of square integral functions. But you could also have other notions for the metric here. And then you have a separate class that represents the elements of this function space. And you know, of course, that if you want to run it on a computer, then you have to discretize it. But the idea is that the space should not have this hard-baked, but it should be made as a separate decision. And yeah, for me, this has mostly theoretical advantages. So one of the advantages is also that it doesn't even need to be just an array. So one practical thing is we also have a class for product spaces where you can actually have multiple different spaces. You kind of have a list of arrays in there, but it could also in principle be something like adaptive resolution. That's something I would really like to implement, but never have time. Where this element of the space would actually first contain a tree where different regions in the space could have a different resolution. So interesting to do, but it also has a very concrete advantage for the topic of this hackathon, and that is that you can easily swap out the implementation of the errors that you have without user code making much changes, at least in theory. That's always a dangerous thing to say. Yeah, I should also say a bit more that the operators are also elements of a class, and this class keeps in mind what is the domain and the codomain, what it's working on, but I won't actually talk that much about here. Now, PyTorch, we've heard a lot about that today, definitely. Specifically, why we last year started going into the direction is, yeah, that it's performant, of course, that it allows having a pipeline that is not purely traditional algorithms, but it could also have a neural network as part of the architecture, or the other way in the world. It could wrap an operator, so it can be used inside of a neural network. And PyTorch specifically is just a popular choice, but it's also attractive because it resembles libraries like NumPy a bit more than, for example, JAX does with its JIT focus. Although this is not necessarily so much of an advantage in the long run, but yeah, so definitely we decided to try going this route. That, as I said, we should be able to replace NumPy, which is what ODL always used as the internal representation with PyTorch. And so again, we heard a lot today about how concretely to enable libraries like ODL to work with PyTorch, but I'd like to also think of it a bit conceptually what we're doing here. So in Python, the way you can write code that works with different implementations is basically duck typing, as C++ programmers might call it in the template world, where whatever library implements a function called, for example, the plus operator or the shape, will just be used on the object that you have. And kind of a more principled way of doing this is polymorphism that you also have in languages like Java, where you first define the classes that allow you to have operations like this, and then any subclass of it will support the operations with whatever internal state it happens to use for that. Would also mention that you can do in more functional programming language something which is perhaps more closely to what we think of mathematicians when we talk about these things, that you have abstract data types and
operations that these data types should support, which don't need to be methods of a class that are invoked by saying object.method name, but instead it's more like when you talk about axioms of a vector space. So this is something in Haskell it's called type classes, in Rust it's called traits. We don't do this here in Python, but it's I think good to also think that there are other ways of doing it. What we actually do in ODL is kind of a mixture of these first two things. So in many cases, as we know, you can actually have code that was written for NumPy and have it with no or very little changes work also in PyTorch, but it doesn't work always. And in particular, in case of ODL, it sometimes quite fundamentally can't work. A principal way of doing this OO column in the middle that I have would be what we also had today, the Python array API. But in particular for that topic, we also heard quite often it should ideally allow code to be usable in these different things. And that definitely works well for basic numerical linear algebra, but ODL does a lot of things with NumPy that just doesn't work at all with PyTorch. And this particular concerns mutable updates to individual elements of an array. And that's something that ODL does very consequently, much more probably than most other libraries, is that even for something simple, like if you multiply two vectors pointwise, then you prefer to use an output argument for this. So the memory has already been allocated at some other point. This is particularly an advantage if you have an iterative algorithm, as you usually do when you are doing inverse problems. But this is in particular also very important for hydrodynamics or this kind of stuff where you really want to use all the memory you have available. You don't want to always allocate new. And that's why ODL had in the form, in the current version really, a very strong focus on always trying to use these out arguments. And in fact, it even generates internally new output arguments when the user does not declare it. So if you, as a user, write the multiplication of two ODL objects, and internally it will actually generate an output argument, which in the normal case is basically the same that NumPy already does. But if you then had a loop over that, then it would give the advantage that you don't allocate over and over again, but instead it just reduce the memory that's already there. The problem is, in PyTorch, it kind of works, but it's slow. And the reason it's slow is mainly because PyTorch tensors are not really just just arrays, but they also have all the machinery that's necessary to do backpropagation on them. And I find it actually remarkable that you can even write code like this and have it work, because when you do element-wise updates to an array, then you would think you kind of break the whole graph. But actually, it kind of does some magic to make it work, but it's slow. So yeah, we could do it like ODL always does and use PyTorch for this, but it's really a performance penalty that's sometimes it's not so bad, but there are many examples where we see that it's just twice as slow, which is no good. And so that's one quite fundamental thing where we can't just replace the old NumPy code with PyTorch code and expect. There's another thing that's a bit of a maybe silly topic, and that's that ODL at one point decided that it would be a good idea to allow people using their NumPy code with ODL. So because it's kind of counterintuitive for many people to have all these abstraction layers and so on. And that meant that you can actually in current ODL version do stuff like you call a NumPy function on what's actually an ODL object. But that, of course, is very fundamentally tied to NumPy. In particular, this is something called array ufunc. And yeah, this is just something PyTorch does not offer. But we decided that this is not such an important functionality. In particular, when people anyway are used to using other libraries that don't have this, then it's not important. So basically, we just abandoned this. And yeah, so that's one of the things we decided, that we would not use these area functs. And we also decided that spaces should have the option to do these in-place updates, which can be efficient, in particular for memory users. This is also relevant for GPUs. But if you're going to do neural networks and want back propagation, then it's just a no-go. And yeah, the other thing is that this is what William Jan talked about, that ASTRA now has pretty good ways of that when you're calling this forward operator, that it can itself decide whether it should make a copy and so on, and then do the appropriate thing. So yeah, just a short thing on this mutability decision. So now the space classes have a notion of which ways of doing numerical operations are supported, and then every space can again either do the in-place updates when that's deemed efficient or not do so. So just to show an example for how this actually works in practice, this is a simple denoising problem. And yeah, as I said, we first declare space, and then we have certain elements, which in this case just load some image files of photos. And I can't go on all the details, but if I run this, then we will see that it sequentially removes the noise. I should probably not go into so much details. And in the development version of ODL, we can now very easily here, when we declare the space, at one point say, now the implementation should be PyTorch instead. And the other code basically doesn't change, although there's one thing here around the actual iterative solver. I now tell it should not do any differentiation, because in this case we don't need it, and it would just use up memory that we don't want. But so that's a quite minimal change, and all the actual operations that might be a bit difficult to do, because they're wrapped in these abstract classes, the user doesn't need to care whether it's in NumPy or whether it's in PyTorch. On ODL just handles that. Yeah, and basically in the similar way to how you switch to backend, you could then also specify a device for the space, and automatically any element of the space that you declare will put it on that device. So you don't need to also copy between the devices. Yeah, in the future, we want to also focus on this batching. Again, there's some people have mentioned that before, that if you're going to do neural networks, then you might not be content with having each input by itself, but you want a mini batch of it. And this is, yeah, we're not very far in how to do this, although to some extent we can again hook into this spaces. We could say the space should also just declare the batch as an on dimension, but that's probably not what we're going to do, because it's kind of not mathematically relevant at the level of the space. So probably it will more look like that every element can have a batch. That also has this problem. So this is still unclear. Yeah, and then of course we could also go to something like JAX, numeric, and so on. We could also do something where it handles multiple GPUs, but that's again the future ideas. Yeah, I suppose I'll end here.